time today talking about the different types of silicon that AWS has designed and developed in the cloud, and for the cloud in particular. But we also use our own cloud to actually develop that silicon itself. So I'm really excited to be joined by two folks today, David and Ahmed, who we're going to talk a little bit here about how customers can actually use our cloud to develop silicon. So it's not just about our silicon in the cloud, it's about how you can use our cloud to develop silicon. So I'll let David and Ahmed introduce yourselves. So David?
Yeah, I'll start. Dave Pellerin. So I drive the semiconductor solutions for AWS, help our customers and our partners deploy electronic design automation, but also other workloads in support of semiconductor design and manufacturing. Ahmed.
Ahmed Elzeftawi, I'm a partner solution architect. I focus on semiconductors and specifically EDA workflows. I work with the EDA, ISVs, and SI and GSI partners that are building solutions to help customers migrate EDA workloads to AWS.
Maybe we should also say what EDA is for anybody out there who's we use a lot of acronyms, right?
Yeah, so, for sure. And maybe I'll start on that. You know, if we think about that full life cycle, and we heard some of that this morning from the speakers, James Hamilton and others, about how you go from a design specification, from concept to an actual working device. A major part of that is involves software for simulation, for verification, design rule checks, power analysis. There's many applications, discrete applications. And collectively, those are known as electronic design automation tools. And even out to things like printed circuit board design, right? Interactive tools as well. So it's a fairly important domain for semiconductor design and manufacturing.
So what are the major challenges today with silicon development or EDA, and how does AWS Cloud help with that?
Yeah, you know, if I can show kind of the supply chain for semiconductor, it's important to put EDA into the context of this whole process. And as a former software developer working on EDA tools, it was interesting to compare what happens in software development to what happens in EDA or chip design specifically. In the software world, you write maybe in Python or Java or C if you were like me. You compile it, you link it, you have an executable that you can then test, and that may actually take you minutes or in some cases even seconds to accomplish to get that instant gratification of an application. For silicon design, though, the challenge is that going from a design language for hardware to actual working silicon that you can test can be a months-long process, or in some cases years long. And so you want to compress that as much as possible by using high-quality simulation tools, verification tools, logic synthesis, emulation, lots of different ways to pull that schedule forward. But at the end of the day, it's a hard problem.
And I think, you know, just to give an idea, right, we've talked about how fast AWS has developed Graviton, introducing 3 generations since 2018. But even within that, you can think about the design level process, how long it is, even within, you know, something that is very, very fast in that silicon business. I think that can give people an idea of, you know, the complexity of what we're talking about with silicon and with EDA and doing design. Maybe the other thing we could also, as you talk through this cycle here, can talk a little bit more about what happens with and why folks use the software and how the cloud can help them do that a little bit further, you know, and what tools we have to help customers.
Yeah. So, and I'll turn it over to Ahmed for more details. But you know, if you think about simulation at the front end, sometimes that's interactive. You've got a piece of a circuit or a digital design that you're trying to, you know, determine that it's functionally correct interactively. More of the compute that happens in simulation, though, is more batch-oriented, where you're running big regression tests or simulations that are system level or analog and mixed signal. And that can go for quite some time with many team members contributing different parts of the intellectual property. And then there's a back-end process of physical verification that's getting harder and harder. Timing analysis, design rule checks, those sort of pre-silicon checks for sign-off before you go to manufacturing. And maybe you can describe in more detail what that looks like from an implementation perspective.
Yeah, absolutely. So as you said, David, the process actually goes through like stages, right, or different phases. And in fact, they are not like just progressive. There is actually iterations, and during the process, you actually go back as well. So as David said, we start with design specifications, maybe trying to define at a high level what your building block or what your design needs to behave or how it needs to behave. And then eventually you try to add more details into that implementation. And then after that, you actually start testing and validating that with simulation. And simulation, this is where you start to need more compute. Verification typically goes, I would say, depending on what you're trying to really to verify. There are at least three different categories of verification. Functional verification, obviously the name implies you're trying to verify the functionality. And then there is another method called formal verification, where you're actually trying to prove that the design works mathematically with some properties that you define for your design to behave to or not to behave to. And then there is also, depending on the content of your design, if you have analog or maybe mixed signal circuitry, then that's where analog or mixed signal verification comes in. And then after that, for your digital building blocks, you go through a synthesis stage, which actually translates that code that you wrote in these descriptive languages, Verilog or System Verilog, into actual gates. Now we are actually going into the manufacturing phase. You have actually selected the process that you are going to use, the foundry that you are going to manufacture your chip at, and now that translation process is the first stage of getting these details in. And then after that, you actually convert that logical representation into physical representation, right? And then this is where you start to do actual implementation, place and route, and then timing analysis, power analysis, and then extraction, parasitics, trying to understand the impact of the physical geometries and the actual manufacturing process on the design. Obviously, there could be iterations in that process, right? Like, for example, after synthesis, you found that your timing has impacted so much or degraded so much, so you go back to your code and re-optimize and things like that.
So it's clear that the chip design and building process is super complex, and customers are leaning on the cloud more and more to develop their silicon and run their EDA workloads in the cloud. What are some of the benefits that they're seeing from AWS?
Sure. Well, let's think about the complexity of chips today. So Graviton 3, for example, 55 billion transistors. So the verification challenge of that is enormous, and you could see tens of thousands of compute cores running for hours and hours, days, weeks at a time, right? To make sure that chip is functionally correct. These are massive verification runs, high performance computing problems. And then back in the manufacturing side, there's computational lithography that happens, big workloads. So kind of those opportunities for cloud is to pull in that schedule, either get the jobs run faster, right? The verification jobs, these high performance computing jobs, or run more corner cases so that you can detect more potential problems with that chip before it goes into manufacturing.
Yeah. It sounds like this is a very compute intensive process, and it could be very expensive if you try to do it on your own. Also, just the amount of servers that you would need to just run all these simulations up front.
Yeah, absolutely. And you think of the trend in semiconductor design in the last 2 or 3 decades has been to become fabless, right? Where these large semiconductor companies no longer have to own their own fabs. They can have engineers, they can have marketing people, lawyers, I suppose you need if you're in a chip business.
Everyone needs a lawyer.
But they don't need a lot of capital to do this. Yeah. But with the compute challenge of electronic design automation, they've now become capital-intensive companies because of those data centers they need. Yeah. So it's a natural migration to cloud for these organizations.
And it's also, to use the word I've used all day, it's also efficiency as well. It's, if you have to acquire lots of physical resources in your on-premise to run occasionally, right? I mean, you max out the system. This is a lot of equipment that has to happen. And I think Dave Brown at the beginning of today talked about one of the things we were trying to do is make sure that we have compute at scale available to customers. And now that we're talking about these EDA or these developing silicon in the cloud, this is kind of the ultimate in that, the ability to scale for customers.
Infrastructure on demand.
Right, there you go, infrastructure on demand.
Yeah, and some of these applications, as I said, they're incredibly compute intensive, and getting scalability for these and high performance is just critical. And Ahmed's been working with customers across this domain and has some performance benchmarks as a result and experiences with the customers.
Yeah, exactly. I guess before going into this, right, I think there was an idea on like trying to explain a little bit this concept of the cluster for running EDA workloads and how it looks like and all that, right? I think let's maybe touch upon that quickly, right? So that make sure that again everyone that's following us is getting the full picture. So typically it starts with users have their own laptops. They have like a thin client on that. Typically that client essentially just gives them access into a compute cluster using a remote desktop type environment. Right, and then that is actually running on a server that's now part of that cluster. That cluster would have a layer for administration, authentication, directory services, if you will, license management, and then commonly a process scheduler. Right, that's very common in the EDA world. And then underneath that, you would have this compute layer, right? And typically on-prem, this is where your static servers are, and depending on like how frequently you refresh these and all that, you could be 1 generation or even 2 generations behind the latest models, or you maybe have a mix, like 1/3 of your cluster is like new, but then the other thirds are old and so on, right? And users, when they submit their jobs, they don't really have that control, right? They just submit the job to the scheduler, and scheduler allocates the job to a certain server depending on what's available, right? But then underneath that, the final layer of that cluster is typically shared file storage, right? And shared file storage is very crucial and important in EDA workloads, right? So in AWS it looks similar, but the reality is the primary benefits that we typically see customers when they initially try to do like a lift and shift type migration into AWS is that they would take advantage of these different instance types that we have across our EC2 family and now try to shape the actual compute that they are going to use to the workload, right? So rather than having just any server that's available and just run the workload on it, to pick and optimize. So for front-end verification, we're going to pick, for example, the C6Is, maybe the M6Is or C6As, or those that have, the highest performance or highest clock frequency. Typically you don't need as much memory per core at that point in stage. And then as you go back to like back-end design phases, like physical implementation or timing analysis, power analysis, this is where you need more memory. And then you get to pick other families, like again, the R6Is, for example, or X2I EZN that has shined recently.
Yeah, I think this is also a great example of what is available in the cloud for customers. If you can take advantage of some of our high frequency instances. We talked about the X2I EZN work here, but we've also have the C instances, the C7G with the performance on the Graviton side as well is a great opportunity. But customers know what they're getting and are kind of guaranteed a certain level of performance. And you mentioned, this data setup that you may have in your own on-premise may not be able to keep up with that, or it may be very different from, we have different types of equipment as well that are here. So I think that's also key to how we're doing it.
So we talked a lot about verification so far, and I understand there are also workloads in manufacturing side. We've heard the term OPC before. Can you explain what that is?
Yeah. I'll give it a crack and then...
Absolutely.
Yeah, so the challenge in manufacturing when you're at advanced nodes, 7 nanometer, 5 nanometer, and soon below that, is you're trying to use a lithography process, right? Shining light through masks to expose the surface and create that chip. The problem is our geometries are now so small that they're smaller than a wavelength of light. How does that even work, right? So optical proximity correction is a high-performance computing workload that predicts the behavior of light at that levels, and so we can make adjustments to the shapes that we're trying to lay down. It's just crazy physics that go on now in manufacturing of chips.
Yeah, so speaking of that, I guess definitely we're talking about that, scaling benefits on AWS, right? And in this exercise, this one, we worked with Synopsys, with their application called Proteus OPC, right? And we picked a realistic design, right? And we started with a compute cluster with a scale of 2,000 compute cores. And initially, that first run literally took days to complete, right? And then we tried to see how further up can we scale this compute cluster to essentially see how efficient we can get the benefits of scaling up and reduce the runtime. And at the same time, we didn't want like any scale. We actually set a metric for us to make sure that we are going to get at least 90% scalability as we add more compute resources, right? And we're able to scale that up using on-demand instances, as you can see on the chart, up to 24,000 compute cores for a single run, right? This is a single mask. So now imagine the chip that we were talking about. This typically has maybe 15 to 20 different layers, and you need to do this process for each one of these layers. And these, I'm talking about the layers that are actually exposed to the end user, that is actually running or creating the physical layout. The foundry, there are actually additional layers behind the scene that they put in between, but let's just ignore these. I'm just talking about the typical layers that are exposed to the end
It's already
designer.
complex.
Yeah, exactly.
Right?
It's crazy complex, right? So now imagine that like each one of these layers with 2,000 cores, which is not small, right?
No.
Each one of them needs days to run. So now see the benefits or productivity improvement that you can get by reducing that essentially into 4 hours. That's what we got when we scaled it up to 24,000 cores. And with the on-demand instances, we were able to get that all the way up to 98% scalability. And even with Spot, including all the interruptions that could happen at a large scale like this, we're able to get it down to only 97% scalability. So the delta was not actually substantially less.
These are kind of, I think, the EDA space, the size of the compute, the size of what's needed to do the verification is almost unparalleled in some of the other high workloads that they're doing. I think sometimes we don't necessarily grasp what goes into all of the silicon development that's here, including this the wavelength of light stuff, and things, the complexity of that. But just the idea that you can scale to have 24,000 cores. I think that also speaks to the size within the cloud or the scalability within the cloud.
Absolutely.
What's been really fascinating to see is as customers are migrating to the cloud for EDA workloads, is they're coming to us often with the hardest problems, the high memory, high scale, problems right before tape out. Tape out's when you finish that file, you turn it over to manufacturing, right? Schedule critical, business critical applications right before tape out because they need the scale, they need the certainty that they can deliver that chip on time to the foundry. It's really an exciting time to be in this space.
Yeah. I mean, and I think you alluded to before, even if you look at the complexity of our own chips going from 30 billion to 55 billion transistors, all of that has to be checked and verified, and that's the process here as well.
Yeah. Let me show you another example in terms of scalability, right? I think that was also, because this example here that we have on the screen is more for a back-end workload, right? And we actually mentioned this a little bit, but again, just to clarify, when we used Spot here, the idea is obviously to take advantage of the cost savings that you can get and achieve, and that was the whole point, to actually see how much we are going to lose in performance with the interruptions and so on, but obviously the cost savings were substantial, right? The next example that I want to talk about, this is more like a front-end type workload. This is a functional verification, or actually formal verification workload with an application from Cadence called Jasper Gold, right? And we started this with an equivalent of an on-prem compute cluster is only with 12 cores, right? And the way that formal verification runs is that you typically say that for these set of properties, we are going to do an iteration and we are going to try some formal engines on them, and each engine will have a time limit of, like, let's say 1 minute. So that's essentially what happened in this run number 1, which is like the orange column that are on the chart here. And then after that, you go to like run number 2, where you say now, okay, I have proved some properties. Now for the remaining ones that I was unable to prove, I'm actually going to increase my time limit a little bit, right? So maybe like 5 minutes, and do this second iteration. And now when you get to the third iteration, obviously the number of properties you are trying to prove is less, but you have to set like a much longer time limit, right? Let's say an hour, for example, and that's what the green column here. So now you can see with the on-prem compute cluster only with 12 cores, that number of properties that were remaining that you had to prove with 1 hour time limit took 35 hours, right? So now we scaled that compute cluster on AWS to like 96 cores and now 960 cores, right? And with 960, we're able to reduce that green bar, right? You can see that on the slide, from 35 hours right into like maybe 2.5 hours, right? But now the benefit that we have this large cluster on AWS, it actually allowed us to do even another run, right? Run number 4, which is the pink one that's shown only in the last one, right? That's not visible in any of these. So it actually allowed us to prove more properties, and it found actually more security bugs that were in the design, right? So the scale actually here has two dimensions. Number one is that it improved the runtime, but then also it allowed us to actually do more verification. We found more problems in the design or covered more properties in our design.
Yeah, I want to make sure we touch on one thing before we get out of here. Is we've mentioned, or thrown out the names of Cadence and Synopsys a little bit here, but I think the key factor is AWS is customers that come to us choose to utilize tool sets and verification from a bunch of different manufacturers, major manufacturers. I think that the key is that we at AWS have continued to work with all of them to test and verify that. And I don't know, David and Ahmed, if you can speak to a little bit about how we have done that relationship or continue to work on that.
Yeah, we have great partner relationships with the EDA vendors, as they typically are called in this industry. It's Synopsys, it's Cadence, it's Siemens EDA, Ansys, and others as well. And we're also customers of them, of course, with Annapurna Labs and other teams within Amazon. This is a great relationship, both in terms of understanding how to best utilize those tools on cloud, but also how to help inform external customers that are doing the same thing. And NXP Semiconductor and Innovium, Astera Labs. There's many customers actually now deploying EDA in production at scale on AWS and getting these benefits. So it's been a virtuous cycle for us. Yeah, and Ahmed, you work closely with the EDA vendors from a partner relationship perspective.
Yeah, absolutely. And again, one of the lovely success stories is obviously ARM as well, right? We didn't really touch upon that.
Yeah.
And ARM is one of those customers that not only try to go with like the traditional lift and shift model that we described earlier, where you actually build a compute cluster, they actually try to think or rethink how they can actually take advantage of the scale of AWS, right? And there is actually a case study that's published that they actually took advantage of AWS batch in like a multi-region, multi-AZ architecture. They were able to scale up their functional verification workloads to 350,000 vCPUs. So imagine the scale, right? Imagine the productivity benefits, right,
for sure.
of that. Yeah. Right, there is no way you could do this in like an on-prem compute environment where you have to, invest so much in the infrastructure and then, as you said, occasionally use it, right? Yeah. So again, reiterating on the primary benefits of the cloud is really that elasticity or scalability, right?
It's no longer an absurd question. What would you do with 1 million cores?
No,
right?
No.
Yeah.
Because it's now becoming commonplace.
Yeah. And I just want to thank both of you for coming out. This has been a really enlightening conversation about doing this in the cloud as well.
Oh, we enjoyed it.
Yeah, absolutely. Yeah. Thank you for having us.
Thank you both.
You're welcome. Great session. Thanks so much.
You're very welcome.
Thank you.